To know if it's going to rain today, you probably pull out your phone and swipe open an app. But for most of human history, finding out the forecast meant looking down at the dirt. Before radar and satellites, people tracked weather by observing tiny biological machines right at their feet. If you saw a colony of ants suddenly grabbing their white eggs and marching toward higher ground, you knew heavy rain was approaching. Plants served as early humidity gauges. A pine cone, for instance, physically clamps its scales shut when the moisture in the air rises, protecting its seeds from the dampness that precedes a storm. There were auditory alarms, too. As the weight of the air, the barometric pressure, begins to drop, frogs respond to the shift by croaking loudly. It is tempting to dismiss these behaviors as old folklore, but these plants and animals were actually acting as the Earth's original atmospheric sensors, responding directly to physical changes in moisture and pressure. The problem with a pine cone or a frog, however, is that it only tells you what the air is doing in that exact moment. To predict weather days in advance, we needed a way to measure the atmosphere across continents. That continent-wide measurement requires putting instruments in places where humans, and most animals, cannot easily survive, like the freezing, oxygen-starved glacial lakes of the Himalayas. This is an automated weather station, or AWS. It is a self-operating robotic system built to sit in extreme isolation. The slotted cylinders on these masts house sensors that take constant readings of the surrounding temperature, humidity, and atmospheric pressure. Because it draws its power directly from the sun using those solar panels, an automated station acts as an unblinking eye, continuously recording the environment in regions that are otherwise a blank spot on the map. By installing these stations across remote deserts, oceans, and mountain peaks, we gather a baseline of raw, continuous data that reaches far beyond the range of any local biological signal. While the automated stations measure the air resting on the ground, modern meteorology also aims its sensors up at the sky. Inside these massive white domes are Doppler radars. They sweep the atmosphere continuously, bouncing radio waves off water droplets to track the speed, direction, and intensity of storm systems hundreds of miles away. All of these sensors, the automated ground stations and the towering radar domes, feed millions of raw numbers every minute into centralized supercomputers. Those machines run dense mathematical equations, calculating how the pressure, moisture, and temperature will interact and move over the next few days to create a predictive model of the atmosphere. Replacing the closed scales of a pine cone with gigabytes of processed numerical data turns simple weather observation into the predictive science of meteorology. All computing power exists to keep people safe. The Indian Meteorological Department translates complex models into color-coded maps. A yellow or orange weather watch alerts citizens to prepare for hazards. A red weather warning means danger is imminent, requiring immediate physical action to protect lives. The stakes behind these warnings are incredibly high. A few hours of advance notice can determine whether a rural farming community has time to evacuate before a cloudburst pushes rivers over their banks. On an even larger scale, satellite tracking gives coastal cities the crucial days they need to secure their harbors and move populations inland before a massive, spiraling cyclone makes landfall. From watching ants march up a hill to launching radar into orbit, the tools we use to read the air have scaled up alongside us. But the core goal is exactly what it has always been: paying attention to the Earth so we can protect the people